there will be three parts of my talk. So I will first talk about the motivation of our work, which is the Poisson summation conjecture. And secondly, I will talk about integral representation of triple product L functions that we constructed. And thirdly, we will talk about the fiber bundle method and how we are going to use to prove the analytic properties for triple L functions. So I will first start with the Poisson summation conjecture. So I will denote F to be a number field. And AF is a Del ring. And I will first recall the Poisson summation formula for vector spaces. So I have VR to be R to the N and VZ is C to the N. And I have an action of GLVR on VR, sending to VR as VG goes to G inverse V. And I denote SVR to be the Schwa space of rapidly decreasing function. And we have a Fourier transform on the space acting on F. Gamma is the integral over R to the N E minus 2 pi I gamma x fx dx. And this Fourier transform as an equivariant property is the action of GLV. It's determinant of G times R G inverse transpose composed with the Fourier transform. And we have a Poisson summation formula. Which is the sum of gamma in Vz of F gamma is equal to the sum of gamma in Vz Fourier transform of F gamma. So this is the Euro Poisson summation formula for vector spaces, which will be used into a direct case now. So now I will talk about integral representation for standard L functions. For GLN, which is a motivation of our integral representation of triple product function I will talk about in the second part. So this is by Gomon Jacquet. So the main thing to notice is that there's a Fn GLN cross GLN equivariant embedding from GLN to the n by n matrices I denote by Mn. So this generalizes an GM equivariant embedding from GM to GA in Tate spaces. So generalizing Tate spaces, they have integral representation for GLN, and they use the Schwa space for n by n matrices as Mn AF, which is a vector space. So this can be decomposed into the local pieces. And at Archimedean places, this is just a Euro Schwa space tensor with the space of complex port smooth functions for non-Archimedean places. So this space, we have a Fourier transform acting on itself. And we also have a Poisson summation formula, which is the sum of gamma in the F point of the n by n matrices of F gamma which equals to the sum of f point of Mn, a Fourier transform acting on f gamma. So similar to the above z in our case. So using this, so they have a zeta integral, which is an integral representation for S pi of GLN, where this pi is the Caspito automorphic representation of GLN. And so their zeta integral is denoted by ZSFV. So this is an integral over the adelic point of GLN, FG, BG, determinant of G to S plus n minus 1 divided by 2 dg, the normalizing factor, where this F is in the Schur space I talked about above. And phi is in C pi, which is a matrix coefficient of pi. And then they apply the Poisson summation formula to get the global Automorphic continuation. And the functional equation of S pi. So this is an example where they use the Poisson summation formula for vector spaces to get the analytic properties for the standard L functions for GLN. Any questions so far? Okay.
Sorry,
yeah.
What's the relation between the CSFP and the L function?
Which one?
The
yeah, so
CSFP is up to some factor this L function?
Yeah, so in identified computation, this gives the identified L functions for pi. And then for ramified places, they use the zeta integral to define the L functions.
Okay.
Yeah.
Okay, I see. Thanks.
Yeah, thanks. And then they have so generalizing this case, we have the Poisson summation conjecture for Shiffer variety, where this GLN acting on n-line matrices is replaced by a general reductive group G acting on those Shiffer varieties. So I will go into some details. So the conjecture is based on several works by Berman, Kashtan, and Go, L. Laforgue, and Socrates. So the conjecture that for any affine Shiffer variety, Shiffer G variety, X, which what I mean by Shiffer variety is that the G varieties with open dense Fourier orbit. And for any Fourier varieties, there should be also a Schur space, just generalizing the vector space cases. Sx, AF. This should also decompose into the local pieces, which is a product over, sorry, SFV. So local field with respect to basic functions Bx in the local Schur space. At each ramified places V. And also a Fourier transform acting on the short space to itself. And also a Poisson summation formula. It should be written as for x in the smooth locus of x over the f point, fx plus some boundary terms equals the sum of x in smooth locus of x, the Fourier transform acting on f, x plus some other boundary terms. So if we have some restriction on the functions we put in, we can get rid of those boundary terms. So we only have just so this part. So we can just get rid of the boundary term. I don't know how to use the other pen. Okay. So this is still a conjecture now, but there are a few known cases for this. So first one is Biermann-Cartan space. This is based on the early work of Biermann-Cartan. So the name is using that space, the space using their names. So this is due to Biermann-Cartan and refined by Gatsliu and Gatsliu-Leslie. And so this is for a space X, which had the X circuits G followed by the derived subgroup of the parabolic, and X is the affine closure of X circs. So we call this X as Biermann-Cartan space, where this G is simply connected. Split simple, and P is the maximum parabolic. And secondly, there's the triples of Courant spaces by Gatsliu and refined by Gatsliu and Gatsliu-Leslie. And also there's my PhD thesis, Automorphic twisted summation formula. For pairs of Courant spaces. So this is for a space of test functions. This is due to myself. On zero locus of Courant form. And functions are built from physical coefficients of automorphic representations of GLN. And there's also Schubert variety. This is based on Troy Getz. And there's also some special cases by Jiang, Luo, Ingo, Shahidi, Sikorsky, and L. Zhang, and so on. So there are just few known cases. There are still not much, but people are hope to using these few cases known to generalize more examples to have a general picture. So the point of the Poisson summation conjecture is that similar to the Goldman-Jacquet case, this should also imply the functional equation and Automorphic continuation for very general long-length L functions. And using converse theorem, also plus local long length, we should then get the long length functionality in great generality. So this is why we want to study this Poisson summation conjecture for spherical varieties, is to hope that we can prove the long functionality using this way. Any questions so far? Okay, this is the end of the motivation part. So then we'll start to talk about the triple product functions. For triple function. So first, define the triple product function. So like R1, R2, and R3 to be positive integers, and pi is tensors of the three pi i's, where pi i's are cuspidal automorphic representations of GLRI, so at that points. Then the triple product function we are talking about is ls pi tensor 3, which we denote ls pi 1 cross pi 2 cross pi 3. So this is a long length L function defined by the tensor 3. So the L group map from LGLR1 cross GLR2 cross GLR3 to GLR1, R2, R3. See? And the case when R1 equals to R2 equals R3 equals 3 is the smallest case, where their global analytic properties are unknown. So that's why we are dealing with this case, is to hoping that to have a theory established for this triple case. And that's just said in the motivation part, if we have the analytic properties plus converse theorem, so we can, in this case, we can prove the tensor for that functionality. So this is a motivation for this case. Okay, now I'll dive into the ingredients of the integral representation. So I will first start with the groups involved. So I will denote here R and F algebra. And I have the group H is a subgroup of GL23. So H1, H2, H3 in GL23R, which satisfies the determinant of the three components are equal to each other. And then I have this curly E, which is E1, E1, E2, E2, E3, E3, which satisfies EIs are plus minus 1, and E1, E2, E3 is 1. And then I denote Z to be the center of GL2 cross the center of GL2 cross the center of GL2. So then I denote HE to be CUHEH, which is Z cross H mod E. So this is if you know what that is, it's the extension of HE mod E in the sense of code width. The definition is just Z cross H mod E. Then from this, we have two projection maps, P1 from HE to GL2 underline, which I'll denote the underline to be the 3 copies. And then we have another projection map from HE to H mod E. And if we assume Ri are greater or equal to 3 for Ri, we denote Mi to be U1, U2 in Ri minus 2 matrices such that the U1 wedge U2 is 0. So this is a subset of Ri minus 2 matrices that are have rank 1 matrices. And then I denote Mi circ to be Mi minus the 0 point. And M to be the product of the 3 MIs, and M circ to be the product of 3 Mi circ. Okay, so these are the groups involved. Of course, there are like GLR and GLR minus 2 groups I will not mention here. And
Sorry, what's
yeah,
this map you want?
the projection map.
Okay, from and to where?
To GL2.
Which GL2? You have 3 copies.
Yeah, the GL2, the 3, and I'm denoting the underline to be the 3 copies. Yeah.
Also, it's P. Wait, no.
Yeah, so it's GL2 cross GL2 cross GL2.
Okay, but sorry, I'm a bit confused. Ah, you quotient out by epsilon.
Yeah.
Okay. Okay, and then you have the second half left. So somehow you. Okay, so the quotient by epsilon only has effect on the z, you think. And then this P1 then goes to like the second factor in Z cross H.
Mm-hmm.
Oh, okay. And then, but it's very similar to P2. Oh, P2 is when you move the epsilon to the H.
Yeah.
Oh, okay. Thanks.
Yeah, thanks. Okay, so then I will talk about some space. So first of all, it's a space Y. I denote V3 to be G2 tensor with GA2 tensor with GA2. And I have an action of H on V3, which is defined above by V1 tensor V2 tensor V3. We have the action of H1, H2, and H3 to be the determinant of H1 inverse V1 H1 tensor V2 H2 tensor V3 H. And this action factors through E and push back along P2 to an action of HE. And then we have an action of GL R minus 2 underline, which are the straight copies of R1 minus 2, R2 minus 2, and R3 minus 2 cross HE, acting on M cross V3. This is preserving M third cross V3 by this our action sending MVGH to G transpose M P1H inverse transpose V P2H. And thus we define some space Y to be a subscheme of M cross V3 preserved under R such that the base change Y M circ is a vector bundle of rank 4 over M circs. Okay, this is a first space, and then we have another space which is called vector induction. In the sense of security rank dash, if you know what that is. So we have XRI is GLRI modeled by RI minus 2 to the unipotent radical of the parabolic, it's a standard parabolic P RI minus 2 to this RI minus 2 block and 2 block. Then XRI is a spherical variety with respect to an action of GLRI minus 2 cross GL2 cross GLRI, which I will not specify this here. And then we define a GA and my circ toaster from we denote VRI circ over XRI cross MI circ. This is equipped with an action R of GLRI minus 2 cross GL2 cross GLRI. So we can show that VRI circ is a Whittaker induction in the sense of security rank dash. And this is the so-called hyperspherical variety in the sense of N3 security rank dash in the relative long-length program they are doing now. And we also define certain stack VRI over MI, which that can be viewed as partial of enclosure of VRI circ. So we have VRI circ is the base change of VRI over MI circ. Okay, so this is the second space. And then since they are both over M, so we can form the fiber product V cross Y over M to V Y. Then we have this diagram. And we denote X to be the product of the XRIs, which is defined above here. So both V cross Y and X cross Y over M admits actions R of GR R minus 2 underline the 3 copies cross HE cross GR. HE is the extension. And then we have equivariant map with respect to this action from V cross Y to X cross Y. And then we can show that X cross Y for M modeled by the derived subgroup of HE is GL R underline cross HE, or I see that GR underline cross HE by HE derived sphere. So this is a sphere variety after modeling out by the derived subgroup of HE. And then we say that this fiber product is a generalized Whittaker induction. Which plays similar role as Whittaker inductions. Or say hypersphere varieties. Okay, so now this is a combination of the spaces. Then we can put the functions on the spaces. So we denote the so we have the space of smooth function of this fiber product over the analytic points, and with respect to some generic character psi to be a space of smooth function. F from GLR, so that points plus Y circ AF to C, such that the F of I R minus 2, the 3 copies, C, sorry, R2, 3 copies, G, M, V should satisfy this is psi of MC, which some pairing from on R minus 2 matrices, F, G, M, V. So this should behave similar to the Whittaker functions. And then we have an action on the space functions. A cross Y, AF, psi. So action is also given by this product of groups R minus 2 cross HE cross JR, setting to the space of smooth function Y cross V cross Y AF, where this action is given by G prime H acting on F G now MV to be F G prime P1 H inverse G naught G prime inverse M P1 H, which is adapting some group actions on the spaces B P2H. So then we can form a theta function, which will later be put into the integral representation with the sum of X MV in X F cross Y circ F, which is an open locus of Y, R G prime H F X MV. So then we have all the ingredients for the integral representations. Then we can finally define the integral representation. So the zeta integral F v prime s prime s naught to be integrate over the direct quotient of GR minus 2 cross the direct quotient of HE cross the direct quotient of GR underline. So then we're integrating the theta functions and also the cast form Vg, v prime, g prime, and some characters depending on s prime, s naught, on g, g prime, h, dg, d, g prime, dh, where SSF, v, and v prime are cast forms on GR minus 2 underline and GR underline. And this eta s prime, s naught are some parameters, are character defined using the determinant of g, the determinant of g prime, and determinant of h, some normalizing factors. So generalizing the Goldman case theory, we have defined the theta integral using cast form and some theta series. So using this integral representation, we have then prove two theorem. So the first one is, again, this is the joint work. For F satisfies certain local conditions. And also the real part of S prime and S naught satisfy some conditions that the first two first 6 parameters, because there are 3 copies, the real part are greater than 2, and the last one has the real part greater than 3/2. And we have the theta integral the f v prime. F is in the Schur space. No, the space of smooth functions, not yet the Schur space. S prime, S naught converges absolutely is equal to the integral of g of he of that points multiplied by the center of he, and the second integral gr minus 2a multiplied by maximum unipotent subgroup of gr minus 2, again also over that points, and gr af multiplied by the r minus 2, also some unipotent subgroup of that point. The integral function defined using some generic characters and associated to the cast form phi and another vector functions p prime, g prime, and also times this f g prime p1h inverse g prime transpose and not p1h. This is after the group actions 2h and then eta s prime g prime h dg prime dh. So after unfolding, we can have this theta integral equal to an Eulerian integral, which can be factored into local pieces. So we can compute in the unramified case. So state the unramified computation result. Assume pi prime and psi unramified. And we take what we call the naive basic functions, which is similar to the true basic function we want, but not yet. I will say more about that. So at the moment, this is defined analog to the characteristic function. Of the integral point, similar to the Goldman-Jacket case. So at the RFI space of smooth compassible functions, their basic function is a characteristic function. So we have theorem 2. Which is for real part of S, real part of S prime, and real part of S naught. Satisfying some conditions. The zeta integral, the local zeta integrals, so which are defined by those integral functions, which are normalized to be 1 at identity. The naive basic functions, and again the parameters S prime, S naught. So this is a sum of K in positive integers, and L is 0 to infinity, and Q minus L S naught. The product, the three product of the Rankin-Selberg of functions, and the sum of -2 minus 1 to the n, a true polynomial, and 0, 0, and n minus L minus Ki, which alpha I, where alpha I is the static key parameters of the pi i's, and trees, which are alpha I prime, which are static key parameters of the pi primes. Q minus NSI prime minus KISI. So using this, you can already see the triple product of function you want, which is a corollary of this. So assume pi prime are tempered, and that epsilon is greater than 0. This is not a group E. This is some arbitrary small thing. And S prime satisfies some condition greater than 1 plus epsilon. Let's see W prime be naive, maybe. Okay, S prime S naught divided by the triple R function we want, parameterized by S naught pi 2 tensor 3 is equal to 1 plus some old terms of -1 minus epsilon divided by 2 for the real part of S naught greater than 1/2 plus epsilon. So in the RFI case, we see this triple R function we want with some old term, which we are aiming to get rid of that at the moment, but we don't yet have it. But we already see the L function, so that's already partially victory. Any questions so far?
Yeah, so is pi prime only appear on the numerator? In the corollary?
Yeah. So there's something hidden in here, just old terms.
So you can choose your pi prime.
Yeah.
I see.
So that's why so far we only have this what we call the naive basic functions. We put this naive basic function here. It's to just using the naive thing we can think about analog to the characteristic function. But we should be able to modify it to get rid of this old term. So we have only this triple R function. So this we are doing now.
Okay, thanks.
Okay, so this is one thing we are still modifying. So, but we can already treat this state integral as an integral representation of triple product of functions. So we have this integral representations. Now we want to generalize the Goldman-Jack K case using the Poisson summation formula for superior varieties to prove the analytic properties similar to the Goldman-Jack K case. So so the approach we are taking now is what we call the fiber bundle method. I denote F to be a number field and G to be a redact group over F, and X to be a superior variety for G. So if you are given X and to projection map B1 and B2 of G schemes, the principle of this fiber bundle method is that if we can prove the Poisson summation conjecture for the fibers EIs, we can prove the Poisson summation conjecture for X. So an example for this is basic affine space, which are due to Berman-Kashtan. Is that if we have G equals GL3 and X is B, we do in R3 cross R3 too, such that we do V is 0. We have this X P1 to GA3 and P2 to GA3 too. So the fibers of PIs are genetically GA2 toters with school symmetric parents. And the fiber bundle method should implies a Poisson summation from the for GL3 and 3 affine closure, which is a basic affine space. And this should be also works for G affine closure with G split simply connected. And N is a maximal unipotent. So this is a guiding example. So we can then try to apply the fiber bundle method to the case at hand. So we have the fiber product we cross Y over M. We have two projections, P2 to V3, which is GA2 cross GA2 cross GA2. So the general fiber of P2 are Whittaker inductions. And general fiber of P1 are vector spaces of rank 4. So since this is vector space of rank 4, so we already have a known Poisson summation conjecture formula and Fourier transform stuff. And then we can make use of that. And for the fibers of P2, we are working on to prove the Poisson summation conjecture for fibers of P2. For those Whittaker inductions. So the aim is after we complete this Poisson summation conjecture for fibers of P2, we can prove Poisson summation conjecture for this fiber product using the fiber bundle method. So we apply fiber bundle method to use two fibers to combine the Schur space to construct the Schur space inside this space of smooth functions we defined before. And then we should be able to construct the Fourier transform again by combining the two Fourier transform from the fibers and prove it has correct equivariance property. So we can use the Poisson to prove the Poisson summation formula, then we can use it to apply to the integral representation we have. And the hope is after doing all of this, we can get the functional equation and measure for continuation of the triple product functions. And then we can show the functionality for tensor product. This is still ongoing work, this part. So that's all for my talk. Thank you very much.
Okay, thank you very much for the very nice talk. So you can also clap in the chat emoji. Okay, so are there any questions for Pam? Okay, maybe I have a question. So somewhere in the integral, you wrote down this theta, you call it a theta function.
Yeah.
Is there automorphic form in GG prime?
No, I don't think so.
Okay.
We're integrating two cast form against this setup series.
Right, I mean, this theta f GG prime is a function in G and G prime.
Mm-hmm.
And is there automorphic form in G and G prime? Yes.
Yeah.
Okay. Wait, is it? And then it's clear that this is left, say, left invariant with respect to, say, GL R minus 2Q and also GL RQ and also H epsilon Q. Because so usually when I think theta function to prove it's modular, you need to use Poisson summation.
Yeah.
And so here for this theta f, you have Poisson summation, or you use it somewhere.
Well, this part is what we are trying to prove for this V cross Y space. We don't have it yet.
But you don't need it to be like a like an automorphic form.
Like, what do you mean by that?
Because in your integral, you're integrating over these GLR A mod GLR Q, right? These kind of things. So what you're integrating is left GLR Q invariant. So the phi and phi prime, I guess, because they are cos forms, for this theta f, then it's also left, say, GLR Q invariant. And to, like, usually for theta function, I thought to get that is follows from this this wave representation. And then essentially for wave representation to check this, you need to use Poisson summation somewhere.
This is a generalized theta function. We're not using wave representation here. So
sure. There's no wave representation. I mean, you don't even have a vector space.
Yeah.
Okay. But you're saying you don't need like Fourier transform to show the modularity, to show that this is automorphic?
That part I'm not sure. We probably need it, but
or maybe this
the purpose for us is not to prove the modularity though. So
okay.
Yeah, probably we need it. Not quite sure. Yeah, we were not thinking in that direction. So
okay. And also you mentioned this triple product. If R1, R2, R3 are all bigger than or equal to 3, then there's not really much results. So are there some results even for, let's say, GL2 times GL2 times GL3? Or GL2
Yeah,
times
yeah.
GL3
That
times...
that you can use the functionality from GL2 cross GL3 to GL6. That is proved
Oh, okay.
by Kim Shahidi, if I didn't remember it right. But there are the only two cases of functionality tensor product functionality known is GL2 cross GL2 to GL4 and GL2 cross GL3 to GL6. That's
Okay.
all. Yeah.
So if you have like a GL2 cross GL2 cross GL3, then you, then you don't have like you don't have functoriality.
That thing we have functionality. But we're dealing with the case when our eyes are greater than 3 or greater or
Okay.
equal to 3. Yeah.
So where does functoriality in that case come from?
It's from I think it's like the Lawrence Shahidi method.
Okay. And so as long as once you're all beyond GL3, then it's
Yeah,
not
there's no construction, not even the interrepresentation construction. So we are constructing now. So yeah,
okay.
yeah.
And so with this naive basic function, then can you prove the meromorphic the functional equation or meromorphic continuation of this triple product in these cases?
So the
Like
thing is still that we have this other things involved.
these O epsilon stuffs?
Yeah,
Okay.
we are not sure yet if we only have this, we can have the correct analytical properties. But we already have some hope that we can modify this naive basic function. We just haven't finished proving. So yeah.
Uh-huh. Okay. But like the choice of this naive basic function is independent of this phi prime or this pi prime.
Mm-hmm.
Okay. And somehow you think there is a good choice such that the right hand side, I mean the left hand side, like somehow it's really independent of pi I prime.
I think there should also be a ranking Sorbel function problem if we have that.
Okay.
It already shows in here.
Oh, okay. I see. So there's that guy. Uh-huh. So is it only like the sum part that you get this triple product?
Yeah, that's from this true polynomial thing. So
Okay, I see.
you see this? Yeah, yeah.
Mm-hmm. Okay, I see. Yeah, no, I understand. Okay, thank you.
Yeah, thanks.
Okay. Any other question for Pam?